Hi, welcome to Big Data Analytics course. In this lecture, we will discuss about design of Hadoop distributed file system and Hadoop distributed file system concepts. Coming to the outline, the first part we will see design of HDFS. Later, we will see HDFS concepts. In HDFS concepts, majorly HDFS nodes, blocks, HDFS federation, and HDFS high availability. These are all the various concepts related to HDFS. Let us see one by one. Coming to the design of HDFS. In our previous lecture, we already seen Hadoop majorly consisting of the following components. The first one is HDFS, which is a storage in distributed file system manner. Another component is MapReduce for processing, allows parallel and distributed processing. HDFS, which stands for Hadoop Distributed File System, is a dedicated file system to store big data with a cluster of commodity hardware or cheaper hardware with streaming access pattern, what we discussed in our previous lecture. It also enables data to be stored at multiple nodes in the cluster, which ensures data security and fault tolerance. HDFS is a file system majorly designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So, very large files. Very large in this context means files that are hundreds of megabytes, gigabytes, or terabytes in size. So, hundreds of megabytes. So, will be treated as very large file. There are Hadoop clusters running today that store petabytes of data. Then streaming data access is the very important in design of HDFS. So HDFS is built around the idea that the most efficient data processing pattern is a write once, read many times pattern. A dataset is typically generated or copied from source, and then various analyses are performed on that dataset over time. Each analysis will involve a large proportion, if not all, of the dataset. So the time to read the whole dataset is more important than the latency, means computing in reading the first record, that is the streaming data access. Then what about commodity hardware? Hadoop doesn't require expensive and highly reliable hardware. It is designed to run on a clusters of commodity hardware, commonly available hardware that can be obtained from multiple vendors, for which the chance of node failure across the cluster is high, at least for large clusters. HDFS is designed to carry on working without a noticeable interruption to the user in the face of such failures happens. There are some applications for which using HDFS doesn't work so well. That means HDFS is not a good fit even today. Whenever having low latency data access, then whenever there exist lots of small files, then whenever there exist multiple writers, arbitrary file modifications. In these cases, whatever the applications having these, even today, HDFS is not fit. These are all some of the considerations of design of Hadoop distributed file system. Then here, what is low latency data means? Low latency data access. Here, applications that require low latency access to data in the tens of milliseconds range, will not work well with HDFS. So also remember, HDFS is optimized for delivering a high throughput of data, and this may be at the expense of latency. HBase is currently a better choice for low latency access. Then lots of small files because the name node holds file system metadata in memory. The limit to the number of files in a file system is governed by the amount of memory on the name node. As a rule of thumb, each file, directory, and block takes about 150 bytes. For example, if we had 1 million files, each taking one block, we would need at least 300 MB of memory. Although storing millions of files is feasible, billions is beyond the capability of current hardware. These are the problems with lots of small files while dealing with HDFS. Then multiple writers, arbitrary file modifications. So what are the problems with these? Files in HDFS may be written to be a single writer. Writers are always made at the end of the file in append only fashion. There is no support for multiple writers or for modifications at arbitrary offsets in the file. These might be supported in the future, but they are likely to be relatively inefficient. These are all the problems with multiple writers, arbitrary file modifications. That's all about the basic considerations while designing HDFS. Now let us move to the concepts of HDFS. This is the HDFS basic architecture. Majorly what it contains, name node. Then we are having various data nodes. Data nodes are stored in racks. Every rack so contains node wise the blocks. Here you can see, for example, here this is rack 1. So we are having various nodes and blocks. Then rack 2. Then a replication between rack 1 and rack 2. Then here clients may write whatever they require to the respective data block nodes. Those can be stored in the respective blocks. Here you can see a client interacting with rack 1 through write operation. Similarly for rack 2 also. Then name node consisting of metadata, what it contains, name, replications, etc. Then name node interact with data nodes through block operations. Then here data nodes to name node, the interaction through read operation. Then again client in between, so reads the data from the data nodes with metadata operations sent to the name node. Name node is the major one which controls all the operations. This is the basic HDFS architecture. Let us see all these components in detail. So HDFS has a master slave architecture that we discussed in our previous lecture. An HDFS cluster, what it contains, consisting of a single name node, which is a master server that manages the file system namespace and regulates access to files by clients. In addition, there are number of data nodes, usually one per node in the cluster, which manage storage attached to the nodes that they run on. HDFS exposes a file system namespace and allows user data to be stored in those files. The name node also executes file system namespace operations like opening, closing, and renaming files and directories. It also determines the mapping of blocks to data nodes. The data nodes are responsible for serving read and write requests from the file system's clients. The data nodes also perform block creation, deletion, and replication upon instruction from the name node only. Anything through the communication from the name node only. The name node and data node are pieces of software which are designed to run on commodity machines. These machines typically run a GNU or Linux operating system. HDFS is built using the Java language. Any machine that supports Java can run the name node or the data node software. Users of the highly portable Java language means that HDFS can be deployed on a wide range of machines. A typical deployment has a dedicated machine that runs only the name node software. Each of the other machines in the cluster runs one instance of the data node software. The architecture does not runs with multiple data nodes on the same machine, but in a real deployment, that is rarely. The existence of a single name node in a cluster greatly simplifies the architecture of the system. The name node is the arbitrator and repository for all HDFS metadata. The system is designed in such a way that user data never flows through the name node. Yeah, this we already seen in our previous lecture. Nodes majorly with respect to master node, slave node, we are having name node, data node. In between, HDFS is there. Then resource manager, node manager, ARM is there. Is the interaction among all nodes presented in HDFS architecture. The core components of HDFS are the majorly the primary node, that is name node. Then the secondary one is the data node. Again, we are having backup of name node that we will call it as secondary name node. So this diagram shows the HDFS core components. Name node, secondary name node is resided beside name node as a backup. Then below we are having data nodes. More data nodes are there. So only one name node. Then secondary name node is also there. That is the backup of name node. Let us see the nodes in detail. Name nodes and data nodes. An HDFS cluster has two types of nodes operating in a master worker pattern. A name node, which is the master, and the number of data nodes, workers or slave nodes. Name node maintains and manages data nodes. Also records metadata, that is information about data blocks. For example, location of block stored, the size of the files, permissions, hierarchy, etc. Also receives block report from all the data nodes. Then coming to the data node, slave daemons means computing, which stores actual data. Also serves read and write requests from the clients or the name node, and they report back to the name node periodically with lists of blocks that they are storing. These are all the responsibilities of data node. Then secondary name node along with checkpointing. Yeah, this diagram shows here the first one is the name node, second one is the secondary name node. Yeah, each node here you can see we are having edit log, then file system image, edit log, new one. So here temporary during checkpoint. Then secondary name node we are having edit log, then file system image, then file system image final. Now here you can see edit log plus FS image, both are combined. Here you can see the first time copying the FS image for the backup, even FS image final also. Here the role of checkpointing and the secondary node. Let us see the importance of these two. Checkpointing is process of combining edit logs with FS image. Here you can see edit log plus FS image. These two are combined. This is the role of checkpointing, which combines these two. Secondary name node takes over the responsibility of checkpointing, therefore making name node more available. Allows faster failover as it prevents edit lock from getting too huge. Checkpointing happens periodically. By default is 1 hour. Then coming to blocks. A disk has a block size which is the minimum amount of data that it can read or write. File system for a single disk build on this by dealing with data in blocks, which are in integral multiple of the disk block size. File system blocks are typically a few kilobytes in size, whereas the disk blocks are normally 512 bytes. This is generally transparent to the file system user, who is simply reading or writing a file of whatever the length. However, there are tools to perform file system maintenance, such as DF, which stands for disk free, and FSCK, file system check, that operate on the file system block level. HDFS also has the concept of a block, but it is a much larger unit, by default 128 MB. Like in a file system for a single disk, files in HDFS are broken into block-sized chunks, which are stored as independent units. Let us see the example of blocks. Here we are having one file with 380 MB. As per the HDFS default, each file takes 128 MB in each block. Now the 380 MB is divided like this as shown below. 128 MB in block 1, then 128 MB in another block, then the remaining balance is 124 MB that is stored in block 3. Here out of 124 MB, so 4 MB is free. Actually, the maximum capacity is 128. So like that, it can be splitted. So now here you can see with respect to the name node and data nodes, the primary node name node, then data node 1 with the first 128 MB, then a second data node with the second 128 MB, then the third data node, the remaining 124 MB. Suppose you are having one more 128 MB, let us assume. So here the third one is 128 MB, then the excess will be stored in the next node. Like that, the data nodes are increased with each 128 MB block size. Like that, blocks are allocated. So unlike a file system, for a single disk, a file in HDFS that is smaller than a single block doesn't occupy a full block's worth of underlying storage. Just to mention, for example, a 1 MB file stored with a block size of 128 MB means which uses 1 MB of disk space, not 128 MB. The remaining space that is reusable. Having a block abstraction for a distributed file system brings several benefits. The first one, a file can be larger than any single disk in the network. There is nothing that requires the blocks from a file to be stored on the same disk. So they can take advantage of any of the disks in the cluster. In fact, it would be possible, if unusual, to store a single file on an HDFS cluster, where whose blocks filled all the disks in the cluster. The second advantage is making the unit of abstraction a block rather than a file simplifies the storage subsystem. The storage subsystem deals with block by simplifying storage management because the blocks are fixed size. It is easy to calculate how many can be stored on a given disk, and also eliminating metadata concerns because blocks are just chunks of data to be stored. File metadata, such as permissions, information does not need to be stored within the block. So another system can handle metadata separately. The third advantage is Blocks fit well with replication for providing fault tolerance and availability. To ensure against corrupted blocks and disk and machine failure, each block is replicated to a small number of physically separate machines, typically here 3. If a block becomes unavailable, a copy can be read from another location in a way that is transferred to the client. Here, a block that is no longer available due to corruption or machine failure can be replicated from its alternative location to other live machines to bring the replication factor back to the normal level. So here by default typically 3 replications are there for everything. Like its disk file system, HDFS file system check command understands blocks. For example, whenever you can run fsck percentage HDFS fsck slash hyphen files hyphen blocks will list the blocks that make up each file in the file system. That is about HDFS blocks. Then block caching. Normally, a data node reads blocks from disk, but for frequently accessed files, the blocks may be explicitly cached in the data node's memory in an off-heap block cache. By default, a block is cached in only one data node's memory, although the number is configurable on a per file basis. Here, job schedulers for MapReduce, Spark, and other frameworks can take advantage of cache blocks by running tasks on the data node where a block is cached for increased read performance. For example, a small lookup table used in a join is a good candidate for caching. Users or applications instruct the name node which files to cache and for how long by adding a cache directive to a cache pool. So cache pools are an administrative grouping for managing cache permissions and resource uses. Then the next one is HDFS federation. Here the name node keeps a reference to every file and block in the file system in memory. Means that on very large clusters with many files, memory becomes the limiting factor for scaling. HDFS Federation, introduced in the version 2.x release series, allows a cluster to scale by adding name nodes, each of which manages a portion of the file system namespace. For example, one name node might manage all the files rooted under the directory slash user, which says, and a second name node might handle files under slash share under the directory share. Under federation, each name node manages a namespace volume, which is made up of the metadata for the namespace, and a block pool containing all the blocks for the files in the namespace. Namespace volumes are independent of each other, which means name nodes do not communicate with one another. And furthermore, the failure of one name node does not affect the availability of the namespaces, which are managed by other name nodes. Block pool storage is not partitioned here. However, so data nodes register with each name node in the cluster and store blocks from multiple block pools. To access a federated HDFS cluster, what clients will do? Clients use client-side mount tables to map file paths to name nodes. How to manage this one? This is managed in configuration using view file system and the view FS under URIs, that is Uniform Resource Identifier. Then HDFS high availability. This is the important one in the HDFS concepts. So this diagram shows the basic components of Hadoop high availability, that is HDFS high availability. So here we are having failover controller active, then failover controller standby. So then you are having the communications through heartbeat with automatic failover and quorum general manager here. So automatic failover denoted with ZK, then quorum general manager denoted with JN. Here you can see. Then monitoring health of the both NN, OS and HW. Here you can see NN active, then NN standby. Then here DN. That means name nodes, data nodes. Where name node active, then name node standby. Then below are the data nodes. Again here monitor health of name node, then this OS and HW. So to monitor the health of all this. Here block report to active and standby data node fencing. Only obey commands from active nodes. So this is the overall interaction of the components included in high availability. So here also shares name node state through quorum of the general nodes, the communication. Here the combination of replicating name nodes metadata on multiple file systems and using the secondary name node to create checkpoints, which protects against data loss. But it does not provide high availability of the file system. The name node is still a single point of failure. If it did fail, all clients, including MapReduce jobs, would be unable to read, write, or list files because the name node is the sole repository of the metadata and the file to block mapping. That's why name node is very, very important. So in case of in such an event, the whole Hadoop system would effectively be out of service until a new name node could be brought online. To recover from a failed name node in this situation, an administrator starts a new primary node with one of the file system metadata replicas and configures data nodes and clients to use this new name node. The new name node is not able to serve requests until it has the following: loaded its namespace image into memory, replayed its edit log, and received enough block reports from the data nodes to live safely. So it has to do these activities to make name node active. On large clusters with many files and blocks, the time it takes for a name node to start can be minimum 30 minutes or more. The long recovery time is a problem for routine maintenance too. In fact, because unexpected failure of the name node is so rare case, the case for planned downtime is actually more important in practice. Hadoop 2, that second version of Hadoop, rectified the situation by adding support for HDFS high availability. In this implementation, there are a pair of name nodes in an active standby configuration. In the event of the failure of the active name node, the standby takes over its duties to continue servicing client requests without a significant interruption. So that is the advantage of HDFS high availability, which is added in Hadoop 2 version. The following architectural changes are needed to allow this to happen. The first one is the name nodes must use high available shared storage to share the edit link. The data nodes must send block reports to both name nodes because the block mappings, which are stored in a name node's memory and not on disk. Clients must be configured to handle name node failover using a mechanism that is transparent to users. Then the secondary name node's role is subsumed by the standby, which takes periodic checkpoints on the active name node's namespace. These are all the architectural changes required to handle this situation through HDFS high availability. There are two choices for highly available shared storage. The first one is NFS, that is Network File System, file or a Quorum General Manager, that is QJM. So the Quorum General Manager is a dedicated HDFS implementation designed for the sole purpose for providing a highly available edit log and is the recommended choice for most HDFS installations. Then the Quorum General Manager runs as a group of general nodes and each edit must be written to a majority of the general nodes. We have seen the communication among all these in the diagram. Typically, there are three general nodes, so the system can tolerate the loss of one of them. This arrangement is similar to the way Zookeeper, one of the Hadoop ecosystem framework, works. Although it is important to realize that the Quorum General Manager implementation does not use Zookeeper. Here, let us see the one observation. However, that HDFS high availability does use Zookeeper for electing the active name node. If the active name node fails, then the standby can take over very quickly, just in a few tens of seconds, because it has the latest state available in memory, both the latest edit log entries and an up-to-date block mapping. The actual observed failover time will be longer in practice, around a minute or so, because the system needs to be conservative in deciding that the active name node has failed. Then failover and fencing in HDFS high availability. The transition from the active name node to the standby is managed by a new entity in the system, which is called the failover controller. There are various failover controllers, but the default implementation uses Zookeeper to ensure that only one name node is active. Each name node runs in a lightweight failover controller process whose job it is to monitor its name node for failures by using simple heart beating mechanism for communication and also trigger a failover should a name node fail. Failure may also be initiated manually by an administrator. For example, in the case of routine maintenance, this is known as a graceful failure, since the failover controller arranges an orderly transition for both name nodes to switch roles. In the case of an ungraceful failover, however, it is impossible to be sure that failed name node has stopped running. For example, a slow network or a network partition can trigger a failover transition, even though the previously active name node is still running and thinks it is still the active name node. Then high availability implementation goes to great lengths to ensure that the previously active name node is prevented from doing any damage and causing corruption, a method known as fencing. The quorum general manager only allows one name node to write to the edit log at one time. However, it is still possible for the previously active name node to serve stale reader request to client. So setting up an SSH, that is secure cell or secure socket cell fencing command that will kill the name nodes process, which is a good idea. Also, the stronger fencing methods are required when using an NFS filer for the shared edit law, since it is not possible to only allow one name node to write at a time. This is why the quorum general manager is recommended. The range of fencing mechanisms includes revoking the name node's access to the shared storage directory, typically by using vendor-specific NFS command, and disabling its network port via a remote management command. As a last resort, the previously active name node can be fenced with a technique rather than graphically known as STONITH, which stands for shoot the other node in the head, which uses a specialized power distribution unit to forcibly power down the host machine. Then client failover is handled transparently by the client library itself. The simplest implementation uses client-side configuration to control failover. Then the HDFS URI uses a logical hostname that is mapped to a pair of name node address in the configuration file. And the client library tries each name node address until the operation succeeds. So that is failover and fencing. So this is about HDFS high availability. These are all the HDFS concepts. In upcoming lectures, we will come up with other interesting topics. Till then, stay tuned for latest updates.